One of the really interesting things in the exhibition is creatures that live very, very deep in the ocean, where there is no light. And we've got a sample here, Maggie, of some of the creatures that you particularly like because you study deep sea vents, don't you? So
Yeah.
show me some of the animals that you've got. There's a crab here that is a particular favourite of mine. If we just move
Yeah.
our jars of preservative. Now this is the famous Hoff crab, isn't it? Tell me about that.
Yeah, it's actually not a true crab, it's a squat lobster. But this specimen was collected from hydrothermal vents in the Antarctic from the East Scotia Ridge. And these are really incredible animals because they have loads of extensions on their bellies, which bacteria attach to, filaments of bacteria. And these animals actually feed on those bacteria, so they're essentially farming their food source on their bellies. And the bacteria are using chemicals from the hydrothermal vents where these animals live in order to make food and to grow. And they're in turn the food source for this animal.
And we should say it's called the Hoff crab because it has in effect it has a hairy
Yeah,
chest, doesn't
exactly.
it? Yeah. Like a certain actor that we know. But I mean, this is the amazing thing about hydrothermal vents is that you're deep, deep down in the middle of the ocean, and yet there is this abundance of life.
Yeah, that's right. Most of the deep sea is a very resource poor environment, which relies just on the rain of any type of organic material from the surface waters where there is high productivity. But at hydrothermal vents, the chemicals that are emitted there can also fuel life. And lots of animals have adapted to survive in these environments through developing adaptations with bacteria, because bacteria, they're essentially the primary producers within hydrothermal vent environments. So they can use the chemicals in those vent fluids in order to make food and to sustain ecosystems.
So we have this food web, don't we? So we have various sort of compounds coming out of the vents. The bacteria process those, and the animals, the higher animals, then use that bacteria to feed themselves. Yeah,
Yeah,
that's how it
exactly.
works.
So in the animals, because of this rich food source that you find at vents, you tend to find really high abundances of animals there. And lots of these animals have developed quite intricate adaptations or associations with bacteria in order to survive within that environment. So the Hoff crab, it can harvest these bacteria on the outsides of its bodies, but lots of vent animals also have bacterial symbiotes inside their bodies, which is another adaptation to surviving within a vent environment and thriving within a vent environment.
Right, and the crab we see in enormous numbers, don't we? And
Yeah.
you were talking about this sort of symbiosis inside. We've got some vent shrimp as well, haven't we, in this
Yeah, so we've got
particular
some
jar? So tell me
specimens-
about that one.
We've got some specimens of Rimicaris exoculata here. So these are vent shrimp that live in hydrothermal vents of the mid-Atlantic ridge. And these guys, they have the sides of their carapace is swollen because they have bacteria underneath it. So the carapace is the sort of hard, shelly exoskeleton that these animals have. And these animals can also feed on the bacteria that they have within their exoskeleton. And so because they have this food source, they need to be near the vents in order for the bacteria to be getting the chemicals. And these shrimps are found in incredibly large abundances swarming around vent chimneys. So I think I read that they can be up to 40,000 per metre squared in some hydrothermal vents.
And they've got this
Really-
very interesting adaptation here on their backs, haven't we, near their head, yeah?
Yeah, so these animals are blind. They don't have true eyes, but they have a high concentration of rhodopsin on the tops of their bodies. And rhodopsin is a pigment that you find in eye structures. And some research was done on this, and which showed that this spot appears to be useful for the animals to detect thermal radiation. So it looks like they can use that spot to detect the heat that's coming out of the vents, so that they can, try to find these vents. Because by finding the vents, they can nurture their bacteria, but it also helps them not to get too close, so that they're not cooked by the vents.
So the crab and the shrimp, I've seen pictures of those. Also, I've seen pictures of tube worms, and we've got some. These
Yeah.
are strange creatures. Yeah, we've got some in a jar here as well. So
Yeah, we've got
tell
some
me about
hydrothermal
those.
vent tube worms. I mentioned that some animals have bacteria inside their bodies, and that's the sort of adaptation
Just move that over,
tube
yeah.
worms have. Yeah, so tube worms have gone quite a long way down the evolutionary path of adapting to hydrothermal vents, in that they're very specialised to this. So they have lost their mouth and their gut, and instead they have a specialised organ called the trophosome, which is just packed full of bacteria that can use these hydrothermal vent chemicals. And that's essentially how they survive. So they provide a nice environment for these bacteria, and in turn the bacteria provide them with food source.
And we've got a little jar here, and this has got what I could only describe as saffron, because that's what it looks like. What is that?
So these tube worms are very close relatives of the big tube worms that you find within hydrothermal vents, and these are called sclerolinum. So they're only about 1/4 of a millimeter in diameter, but they can be quite long in relation to that diameter. And the really interesting thing about these is they seem to be really weedy in the deep sea. So we do find them at hydrothermal vents, but we can also find them in other environments where you have hydrogen sulfide gas. So in places called cold seeps, where you have sort of sulfide-rich fluids coming out of the seafloor, but not at high temperatures. Also when you have marine sediments that are really rich in sulfide, and where you have, for example, decaying wood on the seafloor. So these guys seem to like all of that. And yeah, this species, which has a really sort of curly anterior tube region, the species is called Sclerolinum contortum because of that. It seems to have a really wide distribution. So most recently we discovered a population in Antarctica. It seemed to be very closely related to populations that have been found both in the Arctic and also in the Gulf of Mexico. So yeah, it looks like it can use these environments to gain very wide distributions within the deep sea. And the deep sea is a very connected environment, at least for some animals. It appears that, yeah, some animals can get around it quite easily. But even despite it being connected, there are definitely barriers for other animals.
Now, one spectacular specimen you have here is this, what is it? It's a worm, is it, I guess?
Yeah, this is an annelid worm. So the annelids is the true worm phylum, so earthworms are also in that, but they have a really wide, really huge diversity in the oceans. And this one is called a Pompeii worm, and it also lives at hydrothermal vents, and it's called the Pompeii worm because it seems to be very thermotolerant. It lives inside tubes, which it builds directly onto the walls of active hydrothermal vent chimneys.
So it builds a little home, in essence.
Yeah, and this is right at the sort of interface where these very hot mineral and chemical-rich fluids are mixing with seawater. And it's been shown that it can survive spikes of 80 degrees Celsius to 120 degrees Celsius temperatures inside its tube. So for very short periods of time, it can tolerate these incredibly high temperatures that would normally cook an animal. This is very unusual for an animal to be able to tolerate those kinds of temperatures. Bacteria we know can, but yeah, it's very rare for animals.
So all of the ones that you've described here, they're living at vents, which we know to be quite a nutrient-rich environment, don't we? But you've got one from out on the abyssal plain, which I quite like. We've got to show this. This is the sea pig. So this doesn't live near vents, but somehow it kind of survives out in the deep ocean, away from all the goodies that some of these other animals get.
Yeah, exactly. So these sea pigs, they typically live within abyssal plains. So abyssal plains are typically around 4 to 5 kilometers depth, and they're just very expansive parts of our deep sea floor, which is characterized by a sort of sedimented bottom. And within this ecosystem, the animals are generally relying on the rain of organic matter from surface waters. And that's essentially what these sea pigs feed on. So they very calmly walk around the seafloor, picking up any bit of detritus, so decaying organic matter, and feed off that.
Now, the specimens that you've got here are quite special, aren't they? Yeah?
Yeah, so these specimens were collected on the Challenger expedition, which is really the first major expedition to explore the deep sea, and is also the sort of foundation of modern oceanography as we know it. So this was a 4-year expedition in the late 1800s, before which it was thought that no animals at all really lived in the deep sea, because that is such a remote environment from sunlight, which we know to be where most ecosystems on our planet get their energy from. But what the Challenger expedition found was that actually there are lots of animals that still live within the deep sea, away from light. Yeah, and sea pigs were among those found.
It's easy to forget, isn't it, that actually the discovery of hydrothermal vents on the ocean floor is actually quite a recent discovery, isn't it?
It's only about 40 years ago that we discovered hydrothermal vents. Yeah. But in general, the deep sea has been studied for a bit longer than that.